Good morning, everyone. Let me share the slides here until people join. Morning. So I'm just waiting a few seconds here for more people to come in. Can you see my slides? Perfect. Okay. Yeah, I see the numbers are decreasing. I don't know why. I don't know if maybe you have exams. I don't know. Okay, so we need to start from the last point where we left at last lecture. Need to move a little bit faster this time. We spend some time talking about, like, the total energy of a system, and we develop an equation starting from the Euler equation, and we develop something called Bernoulli equation. And the Bernoulli equation that we stopped at last time is consistent of three terms. The first term is related to the pressure. The second one is related to the velocity, and the third one related to the location of the point at the system. And we refer to all these three type of energy as flow energy, kinetic energy, and potential energy. And if you remember, we spent the time driving this expression, and we mentioned that there was 4 assumptions that was important to keep in mind. That this equation of Bernoulli is only valid when we have a steady flow. We have an incompressible flow as well. Frictionless flow, which means that we are not considering the losses in our system. And we apply this equation along the streamline, or where the fluid is moving. Streamline definition, we're gonna actually talk about it in more detail when we get into chapter 4. But those are the conditions that we put together in order to come up with a final expression, what we call it the Bernoulli equation. And we stopped at these slides, which is talking about something called hydraulic and energy grade line. The hydraulic and energy grade line are extremely important to lots of engineers that are basically designing pipeline and designing system that is transporting fluid along, along a long path of, of a pipeline. So as I mentioned, we have 3 terms in the Bernoulli equation. The first one is this term here, which is the pressure, the kinetic energy, and the potential. So this hydraulic and energy gradient line is kind of, plotting those 3 forms of energy, along the pipeline. So if we look at this location here as what we call it the reference point, or we call it the datum, and the datum here is a reference energy level that we select for all the point along the pipe. So let's say, for example, this is point 1. As we go in this direction. So, and this is, let's say this is point 2, right? So I'm gonna basically plot the total energy on the y-axis. So this is the energy. Okay. So at this point here, the location of the point is basically what we call it the potential, right? So the location of this point far from this reference is basically the location of this point, which means that what is the elevation of these points is a physical location of the point inside the pipe. Okay. Now, if I need to measure the pressure at this point, and I put like a piezometer tube like this, right? So the pressure inside this point will be basically B1, right? If I divided this B1 by gamma, and this gamma here is your rho times G, okay? So now I'm converting this into a pressure head. Okay, so the pressure divided by rho g will give you a unit of meter, which means that I can call now B over gamma or B over rho g is your pressure head. Okay, so the term of the potential plus the term of the pressure. So imagine now we have this pressure is equal to this distance here. So this term here is referring to the pressure head. Okay, the summation of these two is a point on something called hydraulic gradient line. Okay, now if I know the velocity at point 1, which is, let's say, v1, and we take the square of this velocity and we divide it by 2g, so now v square over 2g, if you take the unit for this will be also a kinetic head. Okay, so the unit for this term here will be in terms of meter or in terms of a length. So in this case, the kinetic energy can be converted to what we call it the kinetic head. Now, if we added, in addition to the Z plus the potential, the pressure energy, we also added V square over 2G. We call this is basically kind of the kinetic head. And now on this scale now, this point is referring to the energy head of at point 1. Okay, which means that if I plot like an XY plot, and basically this direction here is whatever the location of this pipe is, right? So at every single point, the physical location of the pipe will be representing the potential. Now, if I measure the pressure and if I measure the velocity, I can plot a chart that is describing the total energy inside, inside this inside this pipe for the fluid. Because in Bernoulli equation is assuming no energy losses, right? This is what we said, right? There's no friction losses, no losses, right? We have a frictionless flow. Now, if I want to plot the energy line for every single point inside the pipe, it will be basically a horizontal line, okay? So this hydraulic gradient line for an ideal flow, and this ideal flow here is referring to, the Bernoulli equation at no friction, okay? And basically this is going to be some energy level at the Y scale, okay? Now, if I go from one point to another point, let's say, for example, this point like I here, right? This is your Z. If you need to measure the pressure, let's say measure the pressure to be at this point. So this is BI divided by rho G. So this will be a point on the hydraulic gradient line. And now V square over 2G, you will get into a same point of the total energy. If you keep doing this at every point, you are basically drawing a line. We call it hydraulic gradient line. And this is basically the total energy line. Okay. So what is this important to engineering application? It's extremely important. Imagine you are designing a pipeline, and this pipeline is like hundreds of kilometers. Okay. So do you expect the pressure inside this pipeline to be the same at every point, or the pressure will change? Can you think about that? So if I have a pipeline, let's say, for example, transporting oil or transporting natural gases from, one city to another city that is far by 100 kilometers. So do you expect the pressure to be the same? Yeah. Do you or not? Some people here will say it will change, right? Pressure will change or not? Everybody in the class or the people are following this. So you're going to have some variable pressure. So do you expect the design of these pipelines should be the same? Do you expect to be like, for example, the thickness of this pipe to be the same or not? Of course not, right? So, you know, for example, location of the pressure that is very low doesn't need to be like, you know, very thick, right? So if you, for example, like if you are designing a pressure vessel, or, you know, I don't know if you're taking design of pressure vessel or not, but, you know, if you have like a pipeline or a cylinder, and the cylinder is subjected to an internal pressure, thickness of the pipe will be kind of, you know, somehow related to the pressure inside. Okay, so you can imagine with me, like, you know, let's maybe think about something like this. So I have a point here. This is the other point here. This is point 1, and this is point 2. And imagine I have a pipeline like this. Okay, I'm just exaggerating here, but this is 100 of kilometers. This is 100 kilometers, right? So you might see, like, you know, some of these pipe will go up, some will go down, depending on the topography of the land itself, right? So you might see huge variation of the elevation of the pipe. Okay. Now, if you want to use the hydraulic gradient line to measure the pressure or to design this pipe, so let's assume we have, let's say, for example, a datum here. Datum or a reference point, okay? And let's look at, this is the total energy line, okay? So first of all, in order for the fluid to move from point 1 to point 2, at least for an ideal flow, what will be the energy? What will be the energy at this point? So it's going to be energy I, right? Okay, on this scale. Okay, for ideal flow, what will be this line looks like? For ideal flow, what will be the total energy line? You know, straight line, horizontal. Yeah, all the lines going to plot is straight line, but what I mean here is, you know, the level of this energy will be the same, right? So let's, you know, be precise on our words. It's going to be horizontal line. Agree? Make sense? Okay, so I have a total energy line here, and we call it ideal here, right? So this is not real, it's ideal. In reality, what do you think about this total energy? Do you think, like, you know, it's going to be some losses as you keep going or not? Yes, right? So you might think, like, you know, there are some losses per meter or something like that along this pipeline. So you might in reality see some line like this. So this is a total energy line, but now this is real, right? So with some losses, and this is basically your losses, right? Right? Everybody agree? So you can imagine now we use this, like, you know, reference of total energy line to have an idea about what is the total energy. And now if you have some idea about the losses per kilometer or something, we can draw this line or we can plot the slope. Okay. If I go one step here, where is the hydraulic gradient line? What is the definition of hydraulic gradient line? Hydraulic gradient line is a line below the total energy line by what? By what value? Look at these problem, kinetic head, right? So imagine I have the same pipeline that has the same diameter, and the flow is the same, right? So imagine this is, so let's say diameter is constant, right? Which means area is constant, and also flow rate, this Q, it has to be the same, right? All over the pipeline, right? So can I draw the hydraulic gradient line now? It's basically what? It's basically, again, horizontal line. Now we have from the real. Let's talk about the real value here. It's not curved. It's not curved. It's going to be lower, right? The total energy line by V square over 2G. If I want to plot something that is lower by V2 square over V square over 2G, that means this is going to be my line here, right? So the line here will be something like this. I hope you agree with that. So, and this velocity, this is V square over 2G, right? I hope I want to draw it perfectly. Right. So this value here is like the same. Why? Because it's the same pipe, diameter, same flow rate, right? Something in blue, right? So basically, this is a hydraulic gradient line. Again, this is real, right? Okay. Can I find out now what is the pressure at every point inside this pipe or not? I'm giving you an idea. This is not related to the subject, but this is really the most important piece of information we need to know about hydraulic gradient line. Okay. So now can I find out the pressure at every single point inside this pipeline without measuring the pressure or not? How? We just go, right? We go from any point here to the pipe, because we know that this is Z, so that means this is B over gamma, right? So if this is point, X, so this is Bx over gamma. So I know that this is a pressure value. So you see here, what is the pressure here at point Y, for example? So this will be By over gamma, right? So which point that has a higher pressure is X, right? How about this one? It looks like from the graph is even lower, right? Right? Everybody? Make sense? Are you following this? Okay, so which means that the hydraulic gradient line is extremely important to determine the pressure at every single point in the pipeline. So let's say, for example, I divided this whole map or the tomography of the land into kilometers. So I have this kilometer here, right? This kilometer here, and so on, right? So I can take the values of the pressure in this region. So this is B over gamma, right? So you see, this is I here, this is 2, this is 3. I can divide the whole map into segments, right? And it looks like maybe for this kilometer here, this part here, I need to have higher pressure, right? So I need to have like, a pipeline with a thickness stand out these high pressures, right? But maybe in the beginning here, I don't need that much, right? Maybe in this kilometer here, I don't need the same kind of level of strength of, inside the pipelines. I don't need the same kind of, pipeline thickness, right? So you can imagine from this kind of simple exercise here that this is, and I'm not speaking here about like something that is not in real life. Like this is really what the people are designing pipeline is going through. Of course, there's going to be much more detail about this inclination of these lines and where is exactly hydraulic gradient by the looking at the flow rate in every single piece of the pipe, these kind of things. But it's going to be the same concept. So instead of like plotting or going and measuring every single point, the pressure, you can just draw a map for this hydraulic gradient line and total energy line and determine the pressure inside this pipeline by looking at the tomography of the land or the layout of this piping and so on, right? So, and then you decide about like, what kind of thickness. When I'm talking about like, pipeline that is, extending into hundreds of kilometers, the most important type of cost here is talking about the material itself. We're talking about like, let's say 48-inch pipeline or something like that, or 30, 36-inch pipeline. We're talking about like huge amount of material, right? So the total cost of the piping will be a huge function, a huge function of the thickness of the pipe. Because once you change the thickness by even 1 millimeter over kilometers of of land, we're talking here about a massive change in the cost of these material. So think about it. Okay. So let me go one more step here, because I mentioned to you that we have 3 terms. We call the pressure and kinetic and potential. But let's change this pressure term into something else, like, because B over gamma has to do something with what we are trying to do in our fluid mechanics here. We know that the work is basically force times distance, right? So this is force times distance, okay? So now if I have a pipe like this, a pipeline, and imagine now at any section of this pipe, the pressure here is B, okay? And the area is A, okay? If I want to move this fluid a distance L, okay? So what I'm doing here, I'm kind of creating work, right? And this work is pushing the fluid this distance, okay? So if I need to find out the flow energy, so the flow energy is basically a work, right? And this work is force times distance, okay? Okay, and this force here is, if I have the pressure and I have the area, is going to be pressure times area, right? Times the distance. If this distance L, this will be L. I can say that this pressure times A times L, and A times L is volume, okay? Which means that the pressure times the volume is energy, okay? How about if I divide this energy or monitor this energy with time? So if I divided the energy with time, this will be with time. What is the energy per unit time? Is power, right? So it's basically, this is a flow power here, right? So this is basically, so basically the flow power here will be the pressure times, you remember, is what we call it Q, and Q here is our discharge, right? So this is a volume per time, okay? So imagine now this is basically our flow energy, or the flow energy is, again, the flow energy is pressure times volume, okay? This is volume, okay? Now, if I look at the pressure times volume and I divide it by, the weight of the whole term, so volume over the weight will be what? Let me just add this one here. Flow energy is pressure times, this is volume. I can call it like this so people don't confuse it with the velocity, right? So this is volume. So flow energy per unit weight, this will be pressure times volume divided by the weight. So I know gamma is weight over volume. So which means that this flow energy per unit weight is pressure divided by gamma. So the term that is actually inside the Bernoulli equation is representing basically the flow energy per unit weight, okay? And of course, you can do the same thing as a kinetic energy. Kinetic energy is half mv square, right? So kinetic energy is equal half mv square. If you divide the kinetic energy with weight, and this weight, if you remember, it's mg, right? So if you divided this by mg, so it will be v square over 2g. So again, the term here, v square over 2g, is basically the kinetic energy per unit weight. So it's going to be v square over 2g. And if I do the same thing for, potential, energy is mg GZ, and if I divide it by the weight, which is mg, so I divide it by mg, this will be your Z. So this is again the potential energy per unit weight, which means that the Bernoulli equation, that is equal B over gamma plus V squared over 2G plus Z, is energy per unit weight equation, right? So this is kind of, this is kind of give you an idea about like what we are trying to show here, right? And if you look at every single term of these is going to be head. So this term here will be pressure head. Same thing here, kinetic head. And this will be potential head, okay? So just to give you an idea about why we are doing this in this form, okay? The most important piece of information that I deliver today is it is a way of developing something called the total energy line hydraulic gradient line. Is that the end? Yes, this is very, very nice question. And this is actually very relevant to what we're trying to see here, right? Because lots of people think, okay, how the fluid will move from one point to another point, okay? Is it because of pressure? Is it because of kinetic? Is it because of potential? Okay, what should be the right answer? It's a combination. Excellent, right? It's a combination of three. You see here, when we talk about the the total energy is sloping down in the direction of the flow, right? So the higher the energy, the flow direction goes like that. So which means that I have higher energy, and as I go along the pipe or as I go along the flow, the energy is reducing. And what is this reduction here is losses, right? Every time I lose something, it just, right? Which means that, and please don't forget this ever in your life, right? Energy that is driving the flow is not really one over the other, right? So if I drop some water at the top of the mountain, do you think it will go down or up? Like rain, right? Basically, rain at the top of the mountain will go down, right? What is the pressure up at the top of the mountain? Is it higher or lower than at the at the land? It's lower. So it's basically the fluid will move from a high location, even the pressure is lower, right? And do you think the velocity at the top will be higher than the bottom, or as the fluid is going down the mountain, it's going to accelerate and the velocity will be higher? Right? The velocity increases actually as you go down, right? So it's actually the flow is not going from higher kinetic or higher pressure. It's actually going because of the higher potential, because the total potential at the top of the mountain is much higher than the other rest of the other part of the energies, right? So that's why the fluid is moving. How about the flow that is going out of a fountain, right? You've seen fountains like, in these decorative fountains, right? So the pressure, like, there is a jet coming out and going like this, right? What is driving the flow in this direction? What is driving the fluid in, fountains like this? So you have a fluid like this, and then the jet is going like that. Okay. What is driving the fluid here? Amazing, right? Kinetic energy, right? So why? Because the pressure here and here and here is what? What is the pressure outside here? Same, which is equal what? Atmospheric, right? It's outside, right? So all these are atmospheric pressure. And this Z here is low, and this Z here is high, right? So you have the same pressure, and this Z is low, but the fluid is moving this direction, which means that kinetic energy here is high. That is what is driving the fluid here. Until the point here, the maximum point, what do you think about the kinetic energy here? Is maximum, kinetic energy is maximum or zero, right? Because if it still have some kinetic energy, it will even go up more, right? Which mean what is driving the fluid here? So driving is kinetic energy, right? This is a good exercise, actually. You know, you have to think about it when you are solving this type of problem. So this is more of an introduction to what I mentioned. This is kind of a simple kind of summary to what I mentioned. But in addition to this, you will learn in the thermodynamic course that also there is additional type of energy that we didn't talk about in the fluid mechanics. And this energy could be internal energy, because you might have this fluid that is higher temperature or something like that. So now in this case, we have to look into what is actually that store the energy in the fluid as well. So internal energy is one of them. Okay. So, but here, those are the three energy that we talk about here. And here, this is a mechanical energy, and it's only divided by the mass in this case. So divided by mass. If it's divided by weight, you will see G divided by G, all this equation, right? So we call it the mechanical energy of the fluid. So the three term that we are talking about here is your mechanical energy of the fluid. Sometimes we call it the small e, which is, it's basically, it's not like dividing by the weight, we divide it by the mass, right? But it's the same thing. System that is going from one point to another point is going to be something related to the energy difference. So energy in and energy out is going to be some energy stored in the system if there are some difference between energy in and energy out. How about this for the fluids? What will be the energy at point one, for example, in this case? What will be the difference in this? At this point one and this point two, what will be the energy difference here between 1 and 2? Can you tell me in real life what will be this value? The energy coming in or energy going out, what will be the difference in the energy, where this difference in energy goes? Still in 0. Oh my God. 0 for Trevor. 0 for what? Let me, okay, let's get back to Trevor here. 0 for what? What condition for 0? If it's ideal, right? So, okay, but if there's in real life there is friction, and actually this friction is converted to heat somehow, right? If you keep pushing fluid in a system, and you keep rotating this fluid in the system, actually after some point you kind of measure the temperature of this fluid to be, you know, a little bit higher. And this is what happened actually even in the transportation of oil and gas in the pipeline. Fluid is transporting inside this pipeline, lots of friction happening, and this friction is in energy losses. And we know, and we're gonna know in the thermodynamics that energy will be conserved, right? So energy never been destroyed, like, right? This is a first law of thermodynamics, right? Energy will be just transferred to a different form of energy. Even friction and losses, it will be converted to another form of energy, which is basically heat in this case, right? Okay, so I hope this is clear, and this is extremely, extremely important to your understanding of the subject of fluid flow, okay? Now, if we have a system, right, that doesn't have any heat losses, that doesn't have, you know, right, and it's steady states, right, but it might have other type of losses. So now the energy in and energy out, and again, this energy per unit weight, right, is going to be basically what? So this energy per unit weight at 1, this is the energy at 2 per unit weight. Okay, if I put this on the other side of the equation, so this minus this is going to be, the difference will be the losses in the friction. Okay, how about if I have a pump or a device that is, you know, taking energy or adding energy to the system? Okay, or I have a turbine that is taking energy from the system. Okay, not all the system is just a pipeline, right? So you might have a pump that is added in the system in order to push the fluid, for example, right? And this is all the pumping stations are. Okay, Or I have a system that is flowing, you know, fluid flow, and then at some point, this fluid is converted to a jet in order to push turbine blades. So in this case, I'm converting some of the energy into turbine. So I can write the same equation, but in a you know, considering other equipment added in the system. Okay, so in this case, you know, the loss, the energy one equal to energy two plus losses minus pump head. Again, pump energy per unit weight is going to be pump head. Okay, plus turbine head. Okay, now this is basically our general equation. You see here now from the Bernoulli equation, ideal flow. Now I added this term here, you know, I kind of converted somehow into, you know, the real case, but in a simple form. Of course, I'm not going to look into the what will be the fractional losses and so on. In chapter 6, we're gonna, or 7, I think 7, we'll go back and study how we can determine these losses, how much these losses is. But we can say, for example, now that Bernoulli equation become, you know, the Bernoulli equation for real flow or for the real case will be same equation, but now I'm adding, or the difference between these two, energy in and energy out, will be the losses in friction. And if happened that I have, like, you know, equipment, and this equipment is taking energy from an electricity or something, right, bringing into a pump, that means there is an added energy from outside to inside the system, right? So you will see here that this pump here should be added to the energy one, or on the other side can be in the negative form, right? You see here, this is a negative, the equal sign here. So this pump is adding to the energy, which means on the other side will be a negative value. Or a turbine, and this turbine is taking from the energy of the system, right? Which means minus on this side, but if I put it in this side, it will be positive turbine. So I can put this equation now in general in this format. And if I have a turbine or if I have a pump, I can put this, if I don't have, I will just put these two zeros. If I have fractional losses or a certain amount of losses, I know how much it is, I can just put it in this equation and I can solve the problem to whatever missing parameter or missing information I need to find. Okay, let's look at a very interesting problem here, and so you can imagine how we can apply this type of knowledge into this. I have a pipe here, and this pipe, actually we call it siphon pipe, and this siphon pipe is very well known in a lots of environmental applications where you have a tank, and this tank underground, and you can't really, you know, you want to drain this tank. So basically what you need to do is, like, you are actually pushing a pipe like this and you put it inside. So you're putting a pipe inside the tank, and but for, you know, because of the orientation of the tank and the, you know, the location of this tank, right, and there's no access from the bottom to drain the tank, right, you are kind of, you know, having a pipe that is extending above the tank and then going down like this. Okay, very simple application for that. I don't know if you have tried before or not, but, you know, some people, you know, maybe they have no gas in the car for some reason, and then they need to add it, you know, or you know, so maybe you can help, you know, other person by taking some fuel from your own car and, right, put it in a container and just transport it. So basically what you need to do, you can just get like a hose, and then you put this hose inside your car tank, right, and try to start the flow, and then you can, you know, fill for somebody else, right? I don't know if you have seen something like this before, right? But let me start this problem by asking very important question. When I put this pipe like this, and I have a tank like that, do you think the flow will just start like going inside this pipe and go like this by itself? Right? You try it. You have a sink, fill the sink with water, right? Maybe half of this sink, right? You need the initial starting. I like that, right? You need to do something in order to start this flow, right? That's, everybody agree with that, right? Because this location here is very high compared to the level of the tank, right? So even the energy here is like, you know, Z is much higher than whatever available energy inside the tank, right? So we call this type of pipe, we call it siphon pipe. Okay, so this is our siphon pipes. Assuming that Bernoulli equation is valid. So Bernoulli equation is valid mean, let's say, steady flow, right? So all the assumption is valid, steady flow along the streamline, no friction and all this, right? So assumptions here. So, this is basically steady. Frictionless, right? Along the streamline. What else? I forgot the last one. Incompressible, of course, right? So all this assumption, right? You don't have to really write it down. I'm just trying to remind you with what is those assumptions are. Okay. Find the expression for the velocity V2. So you just need to find out this V2. And I don't know if I have another figure here, but let me just take a picture here of that. Oops. Okay, so let me do something else here. Copy. Okay. So I need to find out this velocity expression here, right? As a siphon pipe, this is the first one, right? So let's solve the problem this way. Okay. So one of the very important assumption we have to make here is, okay, we know that in order to describe the flow, we have to take 2 points, right? And apply Bernoulli equation between these 2 points, okay? He's telling you that this Z is 0. So this level here is 0. And every location here is far by a certain Z. So this level here is Z1. This level here is Z3. This level here is Z2. And so on, right? So let's say that I have a point here. So where is the point I'm gonna take? So of course it's gonna be a point here. So this is point 2, because I need to find out the velocity at point 2, right? So I need to relate this value to something else. Okay, what will be the second point that or the first point I should put, all the condition at? Can you tell me, can you guide me through this? Which point you want to take? Z4, everybody, Z1, anybody, it doesn't matter, right? I'm just trying to show you that it doesn't matter which other point. The most important thing is those 2 points is like expecting, the flow will go from one point to another point, right? So if you selected point 1, I'm fine with that. You can say the flow is going like this. If you selected point 4, you say, oh, it's going like this from here, and then go like that. But as long as you are consistent when you start your analysis, that's fine. Okay. So let's take like Z4, for example. So this is point 1. Okay. Now for point 1, is point 1 is inside the tank? Yes. So V point 1 inside. What is the velocity of point 1? If the point 1 is inside the tank, what will be the velocity of point 1? 0. Okay. Everybody agree with this? It's not going to be, in reality, it's going to be some value, right? But what we can do is we can assume the velocity of the tank. And this is a very valid assumption in all fluid mechanics. So this tank here is a big tank, right? It's like when we are saying tank, that means we are considering this huge area. So this area here, cross-section area here is this area here, area of the tank is huge, right? So whatever the flow rate is going to be only inside this, this pipe, this Q here, right? So if you need to find out the velocity of the tank, you just divide by the area of the tank. And because the area of the tank is something like really huge, like it's massive, right? So you can assume all the velocity in any stagnant or in any tank or reservoir or something, or a lake, right? Even though there is fluid, there's some velocity, but this velocity is very small. So I can consider this V1 to be 0 with a very reasonable assumption, okay? So this is the most important thing here. So V1 is equal to V of the tank, right? And what I mean here, V tank mean the velocity of the fluid inside the tank. Velocity of the fluid inside the tank, right? Now, if I put the the points for this Bernoulli equation, I like to write it this way. So this is point 1. This is point 2. I like to write it this way, right? So Bernoulli equation, I like to write it this way: 1 to 2. 1 here at the Z4, right? So this is the location of Z4, right? So I can say B1 over gamma plus Z. I wanna, okay, because I don't wanna confuse we use Z1 here. Can I write it as I and, okay, if you don't mind. Can I write this I here? So this is 2 Romans here, right? So basically in this case, just to be different from so this B1 here over gamma plus Z1 plus V1 square over 2G equal B2 over gamma plus Z 2 Roman plus V2 square over 2G, right? I can start substituting by every one of these. What is basically, this is a datum here, right? What is B1 over, so this one here. So what is B1 over gamma here? Q1 equal Q2. Yeah, I'll just let's wait 1 second. You remember, like, I think I mentioned this to people like who were asking questions. Let's put our main important, like, let's go in the main roads first, right? Let's go in the main big streets, right? To go from one city to another city, just go in the highway first, and then get into the small street. Like, what other equation, what other variable that you can use in order to be, because sometime you might spend a lot of time on trying to solve a small little relations, and then we might end up, not using this. You are wasting your time. So first important relation is our Bernoulli equation. So B1 is basically what? If you look at this B1 here, is going to be this gamma H, right? So this difference here, right? So you can say, right? So it's gamma H, right? So now is gamma H divided by gamma plus this location here, Z I plus V1 square. We said it's inside the tank, it's 0. Okay, so this is 0 equal. What is B2 here? This is open now, right? So what is B2? Atmospheric, which is, we said we're gonna use 0 before, right? So this is 0 because B2 is B atmospheric, right? And this, we're talking about gauge here, so okay. So Z2 is this is Z2, right? We don't know what this Z2 is, right? Plus V2 square over 2g. Now look at these. What is this? Gamma over h plus gamma over h divided by gamma plus z1. What is this value? Height times gamma, yes. And then divide by gamma will give you h, right? So this will be basically what? The summation of these two will be what? From the datum here. Will be z what? Z1 or Z4. So this distance plus this distance is basically what? This level here, Z1, right? So this is Z1 plus 0 equal Z2 plus V2 square. And V2 here is our V2, right? Because the point 2 Romans here is V square over 2G, right? So I can just get now V2 square, right? Or simply, so Z1 minus Z2 multiply by 2G, and then you take the root square, right? So this is expression for the velocity. See here, now we already get the, the answer for that, okay? He's asking you to determine, right, this velocity if you are given Z1 and Z2, Z3, Z4, you have all the Z's here, right? So it's very simple. If I need to find out the velocity for Z1 is equal 60 centimeter, Z2 is equal to minus 25 centimeter. I just need to find out V2. So V2 here is 2G, okay. And if I put it in meters, so it's Z1 minus Z2. So Z1 is 0.6 minus 0.25. And then you take the root square. So the velocity here will be centimeter per second. So it's 4.08 meter per second. Okay. What other thing he wants? Estimate the flow rate. So now, some people are saying the flow rate is, Q is equal, Q1 is equal, Q2, that's fine. But now he's asking about these flow rates, right? So what is the flow rate in this case? Q is, and he's telling you that the diameter, did he say anything about the diameter of the pipe? The diameter of the pipe is 1 centimeter. D of the pipe, 1 centimeter, right? So Q is equal to area times velocity. I know the velocity 2, so I can get area 2, which is pi over 4. The diameter is 1 centimeter, so it's 4.08. So the flow rate here is, I just calculated in centimeter cube per second, but you can just do it meter cube per second, right? So you can calculate this, it's very simple. Okay, any questions here? Any question, guys? Okay. So let's go to another problem. It's going to be a similar problem, but you'll see here that, I think I already talked about the flow direction and what is the energy, right? So this is a very simple relation to what I discussed with you in, previously in the previous slides. So we have a flow that is coming out as a jet, and it is going at a height maximum that is that much. We don't know what is this value. The water here at 20 degrees C in the pressurized tank, and you see here the air here is pressurized. So you have an air that is pressurized. Okay. In order to create this vertical jet shown in this, assuming a steady frictionless flow, determine the height. So frictionless steady mean Bernoulli equation is without any friction. So energy 1 and energy 2 will be basically, right? So I can say, for example, here, I just need to find out 2 points. I will apply the Bernoulli equation between these 2 points, right? So this is tank. I can, let's say, for example, here, this is your points, because I need to be smart when I select the points. So I have to put those points are at location where I can refer to, or a reference or something like that. So let's say, for example, if I take this is my reference or datum, so I can take the point 1 here, and I can take point 2 here, right? Okay, and also I can, let's find out what we need to do for this equation. So now what we need to do here, okay, I know the pressure, right? And I know this distance, that is 85 centimeters, okay? How can I start this problem to find out H? So H is required. Looks like it's going to be another point here I have to use, right? But let's say, for example, here, how can we determine the relation between, this H here and the other variable that we have known in the system? Okay, anyone? B1 is equal B2. Okay. B1 is equal B2. Are you sure? This pressure point, this here, is equal to this pressure? Okay, guys, you start losing some of the information we studied. Spend a lot of time in chapter 2. Yeah. Why we cannot say B1 is equal B2? Why we cannot say that? No. Why? Okay. When can we say that B1 and B2 in a horizontal plane in a fluid is equal? Oh my God, guys. Okay. When the fluid is the same, the fluid is the same. Oh my God. Excellent, Spencer, right? Hydrostatic, right? So if we have a static fluid, stagnant fluid, this fluid is moving, right? This fluid is actually moving inside this pipe. So we cannot really say that the fluid is static here, right? So we cannot really say the pressure is the same, right? But what we can say is like, there are, some information about point 1, some information about point 2. There are some relation between these two. The energy difference is 0 because it's a frictionless ideal flow and so on. But I can relate, right? Can I say that the assumption here, V of 1 is equal 0 or not? This is tank, right? This is tank. Same thing, right? So V tank is 0. Right? So it's very simple. And this is going to be all the time our assumption is that the velocity inside the tank is 0, right? Although, like we know, it's going to be small velocity, but we say a reasonable assumption that the flow is inside the tank is very small compared to the flow inside the pipe. Okay, so V1 is 0. Now, which points I will take the Bernoulli equation between? Okay, do I know 1 and 2? Do I know the pressure at 1? Yes, I know Z1, right? I know velocity 1, 0. Now, pressure at 3, right, is 0 because it's atmosphere. Z is H, right? And the velocity is at point 3. Anyone? V at point 3 is 0. Why? Because this is the maximum H. So H here is maximum. That means V3 is 0, right? So this is the highest point, okay? So the jet will rise to the highest point until there is no more kinetic energy to push it up. So which means that, so H maximum as V3 is equal 0. I can now, okay, so let me do the same thing here. Well, I don't have to, I can just do that. So I can say Bernoulli equation between 1 and 3, right? So B1 over gamma plus Z1 plus V1 square over 2G equal B3 over gamma plus Z3 plus V3 square over 2G. We just said that V3 is equal 0. This is the highest level. V of the tank is 0 because inside the tank. B3 is 0 because B atmosphere, right? So, and Z1 is at our reference. This is our reference. So Z1 is 0, right? And Z3 is H, right? So this is your H, right? So which means that B1 over gamma is equal H. Okay, very simple. So what is B1? Can you tell me what is B1? The pressure at point 1. This fluid is static, right? You said velocity is 0, right? This is static. So what can I find out the pressure at point 1 now? How can I find the pressure at point 1? It is basically the pressure of the air, right? Plus gamma H of the water, right? So it's basically simple hydrostatic relation that we studied before. And hydrostatic, why? Because inside the tank, I can consider the fluid inside the tank is static, right? So B1 over gamma, B1 here is the pressure of the air, is B of the air plus gamma of the water times H here is 0.85, and gamma here is gamma water is equal H, right? B air here is 75 kilopascal. Remember to make sure that the units are all correct. So 75 times 10 to the power 3, which means that gamma here is 9810. This is 9810, right? So if we solve this problem, so H here is 8.5 meter. See here, it's becoming very simple, simple problem. You make it simple by selecting the right points and you apply the right condition between those 2 points, okay? Okay, so another example is telling you that we have, let me just see here what I have else. Yeah, that's fine. I can let you solve the last one yourself, but let's finish this one here because very important example. So I have losses here, like, you know, I have a pipe, a tank and a jet, and this jet is going like this. So I have a diameter that is 5 centimeter and then goes, you know, bigger to 8 centimeter. I have the pressure here is 100 kilopascal, which is basically our atmospheric condition. He's talking about losses are neglected, which means that the Bernoulli equation in their ideal form is valid, no losses. How about if I said, for example, the losses is 2 meters? What you need to do? Energy 1 minus energy 2 will be equal to 2 meters. So you can just include it in your last example. Adam, go ahead. Put the question. Yeah, you put the question directly on the chat. I will try to answer it. Okay. No problem. Yeah, no problem. Okay, and also, like, if you guys have any, like, you know, if I'm fast or something, you want to stick around after the lecture, we can discuss it, or you can post whatever question. Please make sure that don't hesitate to put the question, because sometimes people have misunderstanding about the concept. The only way to understand if this is what you think is right or wrong, you just put the question. Don't think it's a silly question or simple question. Okay, so losses can be neglected in this problem. Okay. So, and he's asking for what water level. You see, now the problem is getting a little bit slightly, you have to think about other aspects of fluid mechanics. It's not just, you know, what we studied so far. So for what water level H will the flow begin to form vapor cavities at the throat of the nozzle? This is the throat of the nozzle. Throat means the smaller area of the nozzle. And this is a nozzle we have here. Okay. So at which H, how this is, how this is kind of related. The liquid vaporized at, okay, how do you think will happen here? What do you think will happen here? How the liquid will vaporized here? Liane, temperature change is never in our part of this course, right? We're gonna ignore all the heating and other things. Right? It's gonna be heat transfer course and thermodynamics. That's not part of what we're doing here. So most of the time we're dealing with constant temperature system. Okay, how liquid evaporates? Remember, we spent quite enough time in first chapter. Pressure. Remember, when we reduce the pressure to the point, we call it what? Remember these conditions? Remember, we said we can either boil the water by increasing the temperature or by reducing the pressure. Okay. What condition liquid will evaporate at the existing temperature? What this condition we call it? Or what property that we are kind of referring to? Vapor pressure. Excellent, right? So which means that, we need H where the pressure at point, this is point 1, right? Pressure point 1 equal to B vapor, okay? Which means that in another condition, right? You just need to find out B vapor at, this is 20 degrees C fluids, and this is water, or sorry, 30 degrees C. It's given here, right? I just need to find out the condition at 30 degrees C. What is the pressure of B vapor, right? And of course, because you know that it's pressure plus Z plus V square over 2G, it looks like the velocity inside this throat will be increased, right? Because at this point here, what? Z is the same, right? Between point 1 and point 2, same Z, right? What is changing here? It's the velocity, right? The velocity is more here or here at 1 or 2. What is the velocity? Where is the location of the maximum velocity? At 1 is higher because the area is smaller, right? So you can expect like the area is reduced. That means the velocity is increased, and you will see that what will happen in this case, you have a summation of pressure plus Z plus V square over 2G. Now you have higher velocity at one point. In order for the pressure to be changed, that means the pressure will have to be lower, right? So the total energy here at 1 is higher than the pressure, the total energy at 2, right? So the condition here is basically related to the summation of 3 terms, not only 1 term, which means that some of them could be, lower value than the other, right? And the lower value given in this problem is a limits at which, H is 1. So how can I start this problem here, right? It looks like if I put 1 and 2, I don't know what is V1 and what is V2. And I don't know what is, I know the pressure, right? But what other thing that I can do in this case? I can say, for example, I can start between point 1 and 2. Like let's say, for example, Bernoulli equation between 1 and 2, right? I know B1 is equal B vapor. So I have to go to the table A5, I guess. I have the values here. At 30 degrees C, B vapor is 4.2 Pascal. Okay. And remember, this value should be what? It should be an absolute value, right? Okay. So now what is the pressure here? BV. So this is equal B1. So I can put B1 over gamma plus Z1 plus U1 squared over 2G. Can you check, like, for me, if you have the textbook or like you have the table? I just want to make sure, like, I have the numbers correct here. Is it possible? Is the pressure given in this table is absolute or gauge? Can you do this until I just write down this? And then B2 is B2 over gamma plus Z2 plus V2 squared over 2G. Okay. So this is the reference. So this is the datum. So Z1 and Z2 are, if I consider this is 0.2 and this is 0.1, both are the same. I can say both are zeros, right, from the datum. So B2 is atmosphere. But now that's why I'm actually asking this question, that I just need to find out this pressure of vapor. Did anybody find it? It doesn't say. It doesn't say what? Pressure. Okay, just it doesn't say absolute, right? So which means gauge, right? Yeah. Okay. So you just say that. So this is basically gauge, right? So I'm just trying to check, like, because sometimes tables are listed in absolute. That means in this case, you have to take the atmospheric pressure as the 100 kilopascal and so on, right? So here, like, because that's what I'm saying, like, I think it's 100 kilopascal is given in the problem for that reason. So I think does it say vacuum? It's easier for me to 5. Yeah. So those are absolute pressures. Those are property of absolute pressure, which means that the atmospheric pressure has to be taken as 100 kilopascal. So B2 is 100 kilopascal. So 100 times 10 to the power 3. Gamma is 9810. Okay, so I will have to do this. And B1 here is kilopascal, so it's 4242, and gamma here of the water 9810. Okay, so what I need to do here is basically H is gonna be 100 minus 4242. $9,810. Okay. So this minus this plus. So sorry. This is 1 and 2. Sorry. This is between 1 and 2. So I have V2 D1 squared minus V2 squared over 2G. Okay, so this is equation 1. Okay, looks like I don't have an idea about V1 and V2, but I know relation between V1 and V2. Okay. Okay, what else I can do? Looks like 1 and 2 is not really helping that much, because I know V1 as function of V2. So I know the equation Q is equal A1 V1 is equal A2 V2, right? So this is pi over 4. The diameter of point 1 is 5 centimeters. The diameter of point 2 is 8 centimeters. So I can know what is V1 and V2. So I can solve these two equations together. So V1 The diameter one is 5 centimeters, so 0.05 square V1 equal to pi over 4. The diameter is 0.8 square times V2. So I know what is V1 and V2. So I didn't solve it here in my notes, so but you can find out V1 and V2 from this equation. Okay. So what is this giving you is basically the velocity of one, because this is two equations, function of V1 and V2, and two equations of two unknowns. Very simple. You can solve these two equations together. What is the relation between H and the other ones here? So I can find out. Let me just add this. What other point Bernoulli equation between? Okay, go back here. Which 2 points I can put in order to find out H? B1 was B vapor because it's given in the problem. The problem is telling you that find out your H at the condition where liquid start evaporate or liquid start becoming, forming a vapor cavity. So now there is another kind of, implicit kind of given, so not a direct given in the problem, that is telling you that at the throat, liquid will evaporate at this condition, which means that only liquid will evaporate when the pressure reach to what we call it B vapor, right? That's why we put the condition at 0.1 or at the nozzle is equal to B vapor, right? So now I need to find out H, right? So can I put this point here? This is like, 3. And I can say that Bernoulli equation between 0.3 and 0.2. Can I say that? Of course I can, right? So 0.3 is at the water level of the tank, right? And the H, the Z here is basically H. The pressure here is atmospheric, right? So I can say, for example, in this case, between 3 going to 2, right? B3 over gamma plus Z3 plus V3 square over 2G is equal B2 over gamma plus Z2 plus V2 square over 2G, right? It looks like the pressure here is atmospheric. Okay. Z3 here is your H, because this is a reference point, and this distance here is your Z3, which is H. So this is H. Plus, this is a velocity inside the tank. So the velocity inside any tank is 0. Okay, I only take, okay, you see here? Yeah, that's why I expected. I put B vapor here. In this equation, I put B atmospheric at one point and B vapor at another point, right? And I put this in the absolute, so I have to put here in the absolute. The difference has to be matching, okay? When I put here, okay, 100 kilopascal, okay, let me go with what you are saying. So if I put this 100 kilopascal, I'm going to put the same thing here for B2, B atmospheric here, right? B atmospheric here is 100 kilopascal, so it will cancel each other, right? B atmospheric here is equal 100 kilopascal. As long as I know in both sides of the equation where I'm putting my pressure in gauge or absolute, is going to be fine, okay? Makes sense? Everything is okay? Yeah? Okay. So I have H here, if you want to do this way, so this will cancel this, right? Z3 here will be H. And V here inside the tank is 0. So this is 0 plus equal to Z2 is 0 because Z2 as the data at the datum, right? And V2 is, we just get it just, a few seconds ago. V2's, where we get this, I kind of, tricked you here. It's just like, you just need to solve these two equations. You just find out V1 and V2, okay? I didn't solve it in my, my notes here, so I don't have the numbers and I don't have time to go over this, right? But it looks like when I have V2 here, I can get H in meter. It's a very simple problem, except for you have to keep in mind that there are some other information that you have to know about fluids, right? So yes, everything is about Bernoulli equation and the flow energy, right? But there is one simple information that we know about it in first chapter that is talking about vapor pressure. When the liquid evaporate at the same temperature, that means liquid pressure reduced to the point that is equal B vapor. So this is what's solving the whole problem. Okay, I think I will leave the last question here for you to read. I have the solution for this problem. This is a very simple problem, but it's kind of combining what we learned in the whole chapter, talking about Bernoulli equation, talking about momentum, jets, and talking about the forces on a structure. So please go over this, and I think there is other problems similar to this in the tutorial will be solved as well. Okay, I'm gonna stop here and stop recording, and we'll be around for any questions you might have, guys. Okay, let me stop recording.